She's been doing a lot of great work. As some of you may know, she's at Rutgers right now. You've been at Rutgers, it looks like, since 2009, right? Did a postdoc at UCLA, right? And a PhD in civil and environmental engineering at Princeton. So have been kind of all around the place, but now you're back on the East Coast again at Rutgers. Of course, we know the Greenland ice sheet is doing strange things these days, right? We are concerned about it. We've got Asa telling us today about decreasing density and ice layer volume in near surface firn in southwest Greenland's percolation zone over the period 2012 to 2019. So with that, if you're ready to go, you can probably share your screen and start a rolling.
Thank you. All right, I am ready. Let me do exactly that. Thank you so much for giving me this opportunity to talk about my research with y'all. Okay, yes, thank you so much for having me. Yeah, I'm going to talk about something that maybe seems a little bit like, what? Decreasing density and ice layer volume? But yeah, that's what I'm going to talk about. And I'm going to share with you some data from field expeditions that I have done in Greenland in 2017, 18, and 19. And that's me on the picture right there. I'm going to turn on the highlighter and see how that works. Let me know if it looks, I think it's going to look okay. This is me. All right, here I am looking at a fern core. The whole talk is about this kind of stuff, these fern cores, and collected in Southwest Greenland's percolation zone. All right, the motivation for this can be shown in this graph right here. This is a paper by Isabella Velicania and other people that shows the Greenland ice sheet mass balance over the last couple of decades with the GRACE satellite and with mass balance models. And oh my God, it's going down, right? There is a huge increase in or the mass loss, Greenland ice sheet losing mass. And why is it losing mass? Well, mass balance, of course, is the sum of mass being added from snow accumulation and mass being lost by ice discharge and runoff. Okay, and where does runoff come from? Come from surface melting. And some of that surface melting goes to runoff, but not all of it, okay? About 45% of all the surface melt on the Greenland ice sheet never escapes to the ocean. Instead, it infiltrates and refreezes in firn. All right. Well, what's firn? Some of you will know this, but for those who don't know it, I will just briefly explain it. All right, here is a photo from my field site, and we're actually collecting a fern core right there. This is the magic tool to extract fern from the ice interior. All right, I'm going to try and just sort of show you what's going on below here. So here we are. We're pretty small expeditions. We're only from 2017 to 2019, we were between 5 and 6 people. Anyway, what's below us? Well, we have it's snow and ice. All right. So I tried to I put this image kind of below here to try and illustrate what happens to the snow as it is compacted to ice, right? So an ice sheet is created by snow falling over other snow and compacting over time. So at the surface, you have kind of a porous snow layer of the last winter. It's probably not 90% air that we're standing on here, but still there's going to be quite porous at the surface. But then as you go down into the ice sheet, deeper and deeper layers, the overlying snow going to compact the snow below it. So at some point, you're going to come to a place where all the air in the snow is now enclosed into bubbles. And that is what then you have ice. All right. The pore space is closed off. Now, firn is the cool stuff between snow and ice. So firn is snow that survived more than one melting season. And what's really important to know about firn is that it's a porous media. And that means that when you have melt on the surface of the ice sheet, some of that water can then infiltrate into deeper layers of the firn column. And there are some studies that show that it can go as far down as 10 meters, and certainly below the last winter's snow layer. All right, so that's pretty relevant. That's how firn is absorbing some of that huge amount of surface melt. Okay, all right, so where do we have firn on the Greenland ice sheet? Well, pretty much everywhere except the lowest elevation site. This is a graphic from the Polar Portal, the Danish project. The blue line shows the snow line. So that is, this is from 2020, but you'll see variations from year to year. But basically everything above the snow line is snow that survives a melting season, so which is then generating firn. So firn is found over most of the Greenland ice sheet, and it can be up to 80 meters thick. And is not a lot compared to the volume of the ice sheet, but it has still a big potential. And there was a very important paper that came out in 2012 by Joel Harper and others, that they did sort of a calculation to figure out, okay, what is the potential capacity of this firn layer to absorb future melt? And they found that the firn layers in the Greenland ice sheet could buffer global sea level rise for decades to come, which sounds like a great insurance for some of the worst way that Greenland can affect the global climate or global system by increasing sea levels. All right, because it's so much water frozen into ice in the Greenland ice sheet. All right. But then what happened? This was published in 2012, but 2012, if you study the Greenland ice sheet, you know 2012, because 2012 was the, so far, in this modern era, the biggest melt year ever, right? This is where almost the entire surface of the ice sheet was experiencing surface melting. So after this year, there were other expeditions that went to the Greenland ice sheet and retrieved ice cores, like shallow ice cores, showing what's going on near the surface. And there was a study from Horst Machgut and others, and they showed that in the lower part of the percolation zone, where you have meltwater infiltrating into the firn, there have been established very thick layers of ice that were had a very low permeability, almost impermeable to meltwater infiltration, that prevented meltwater to percolate through it. And instead, you had formation of runoff, okay? So you had increased runoff because of this formation of very thick ice layers that was observed after the 2012 melt event. And then, of course, we have this paper by Michael McFerrin and others who took this one step further and used modeling to estimate and mapping where are these we call them ice slabs, these very thick layers of ice that will reduce the permeability of the top layer of the firn. And he found in his paper that this layer would expand a lot in the future with increased melting, and could have a noticeable effect on global sea levels in this century. So this is the motivation for me to study what's going on with the firn in Greenland. And here, I want to show this figure too. This is from your website, National Snow and Ice Data Center, that you guys have put out there together. I think this data comes from Thomas Mote originally, who's using passive microwave satellite, passive microwave satellite data to infer the total melt area of the Greenland ice sheet. And I really, really love this data because I really think it shows something about what's going on and what's been happening in Greenland. So here you see, right, from the late 70s, 2012, this huge increase in melting. And this shows melt area, so it doesn't represent intensity, but I think it's still a very good way to look at this. And you do see this huge melt event in 2012. All right. But look what's happening after 2012, okay? It sort of goes down to another more kind of constant variable level here, right? It's sort of like this whole period is sort of at an elevated rate compared to earlier, but still after 2012, it's sort of kind of starts hovering. So in my work, I want to know, okay, what's happening here after 2012? That's what I'm going to look at in this talk. All right, so what has happened with the Greenland ice sheet firn after 2012? And I'm looking at the southwest Greenland. So I'm going to have a study area down here. And I have a total of 46 shallow firn cores. 19 of them are completely new, collected in an NSF funded project between 2012 and 2019. So, and here's a close-up of all the sites. And well, I basically just want to show you that there's a lot of sites. So we have 46 cores, but they're collected at 15 different sites. And I must say, well, you look at this and you're like, where these names? So every blue dot here is like a site where one or more cores were collected. And I actually used some of these sites other people went to before me, and I'm going to show you those cores too. And I've been reusing site names, and that's why the site names are just all over the map. But I thought it made sense to kind of use some of the existing site names. But anyway, all of these are new. The ones that are labeled A, B, C, D, E, F, and G. Nobody been there ever before to collect cores. So those are super new sites. Okay, cool. All right, whatever I want. There. Okay, great. All right. To tell you a little bit more about the study area, the furthest distance between sites is 120 kilometers from the highest elevation site, EKT, to down here to site A, okay? 120 kilometers. And the elevation distance between the lowest elevation site at CONU and the highest elevation site at EKT is about 500 meters. And what's interesting about that elevation gradient is that, and the study area as a whole, is that snow accumulation is actually quite similar across the site. That doesn't vary between the site. There is variability from year to year, but not a great variability from site to site. So when it comes to snow accumulation, the input of mass, these sites are all very similar. However, when it comes to surface melting, they're very different. There's a lot more melting at the lowest elevation site at CONU than EKT. On average, it's about, I think, double. So big differences in melt input, but not the snow input. Okay. All right. Oh, I want to show you a little video. Let's see if I can start it. Here we go. This is a video from our fieldwork, and it just shows how the cores are retrieved. So you see putting down a barrel. The barrel will fill with firn, and you put a very heavy drill on top of it. And then the drill is attached to extension rods that attaches to the barrel. And then you drill down meter by meter. And so you have to like pull it up. Here we pulled it up, and then we're going to push out the contents of that barrel that now it contains the firn. So here's firn from the Greenland ice sheet coming out on this tray here. this is our data. And then you just keep repeating this process until you are unable to go any deeper or you run out of time. So anyway, what we do with these core sections is then analyze them for density and ice layers. And I just want to show you an image here of some core segments. And I have arranged them here in order, so the ice content is increasing. So you see, so you could see, right? You can see these ice layers here. And you can see here in the fern. So this first layer here is just all fern. And then you come down here and this little section here is all ice. All right. And you can just see how you can figure that out just by looking at it. So we recorded the position and the thickness of all these ice layers. And also we measured the density of all of these pieces of the fern core that we retrieved. And we get data like this. So I'm going to show you an enormous amount of figures that looks like this. Okay, this is the fern core data at the EKT site. This one is from 2017. And so you have depth below surface here on the y-axis, and then density, the x-axis. The black line shows the density, all right? And I put a red line in here so you can kind of use that as a reference, because what you see here is how the density increases with depth. So this is what I talked about at the beginning. This is the compaction of fern because of overlying and other fern and ice layer and so on. So you'll see this like increased density with depth. All right, you see something else in this data, right? These blue lines are the ice layers. So they will show you the position and the thickness of ice layers in fern. So it's just a representation of the core, okay? And what's so cool about core data is that when you go deeper down in the core, you're also going back in time, okay? So we have some dated cores from this region, which is pretty amazing, actually. We even have a couple. So I have a pretty good idea of how the age at different depths. So if you look at the top 10 meters, that has been, that's snow and fern from the last 14 to 15 years. And you go down next 10 meters, you're going to go back 16 to 31 years ago. So here at the bottom of a 20-meter core, that snow, like that's now fern, was deposited about 31 years ago. All right. So we're going back in time by going deeper. All right. Okay. Here. Okay. I know this is crazy. I just need to show you some of all these new cores that I collected. All right. So here's just a sample, actually. Those of you who are quick to calculate, you'll be like, that's not 19 cores. No, it's not, because I'm actually only showing one core from each site. But these are a sample of the new cores we collected. And so here is the EKT at the one end here. That I kind of showed you previously, which is at the highest elevation. And I'm showing you these cores just to kind of hopefully that you'll be impressed of the number of cores we collected, but also to show you that there is a huge change over space, because these cores are organized in elevation. So the elevation is decreasing in this general direction. So site A here is the lowest elevation site that we visited, and then EKT is the highest elevation site. You'll notice the year is actually a little different, because some sites we only went to in 2017, or we only got a core from 2017, and others we got in 18 and 19 and so on. But anyway, I've arranged them all here. And regardless of the fact that there is a variation in year, you can really see the impact of elevation here, like how at the highest elevation you have lower density and less ice layers, and then you go down to a site like this, site A here. Oh my goodness, this is almost just ice, right? It's just a thin layer of fern at the surface, and then it's just ice, and it's very dense, okay? So, all right, but the coolest thing, of course, in doing this work is that I get to, somebody else was here before us. So I like to show this photo here. It's just like footsteps in the snow, because somebody walked this place, many of these places before us, and they were awesome because they saved their data and made it available. So I'm basically following the footsteps of giants, which is pretty awesome. And I just want to point them out. We have two cores that are collected sort of a long time ago in this context. One is collected at Site J by Takao Kameda in 1989. The other is from the Parker project led by Ellen Mosley Thompson in 1998 at DAII. And those are the oldest cores. And I'm going to also show you how things have changed with respect to those two cores. But in addition, I also have a huge number of cores from a couple of different expeditions that are total 25 cores that are collected from, there are a few from 2009 and 2012, and then a couple after that. And those are collected by Horst Mahkut, Mike McFerrin, Eric Osterberg, and their teams. And they're collected all over the sites too. So I have 46 cores, and I'm now gonna show you that all together. And I could not resist putting together this table. And yeah, can you read this table? Okay, it's not, I don't want you to read this table. I just put this up because I thought you might be a little like, wow, that's a lot of stuff. Yes, that's a lot of stuff. And what I just want to point out is that there are a lot of cores. And from some places like CONU, we have a lot of cores from the same location. And then a place like Site A, we only have one core. All right. And so the thing about these cores is that they're collected at different sites. They are also varying lengths. Mostly I selected cores that were at least 10 meters. But for CONU, I'm also going to show you some shallower cores because CONU is a very interesting place. They're also all collected in different years. So yeah, this was a kind of a challenge to put together a data set like this, but I have it. All right, here is some of the data shown as these core profile logs. And I'm not even showing you all the data, but just to give you guys kind of a visual idea of what's going on here. And the main point here is that you can see that in this figure, the data is grouped by site and by year. So you'll notice like here's Site J, for example, and you'll see that you have the 1989 core, and then it's what is 2017 core next to each other. So this figure basically makes 2 points. It shows a little bit, you can sort of discern changes over time, particularly between the legacy cores and whatever core was collected after that. But what you also see here is change of elevation, which I already demonstrated with just showing the new cores collected by the project that funded my fieldwork from 2017 to 2019. But here you see it too, honestly, despite the fact that you have many different years here. You can see that CONU, very different. This is the lowest elevation, and then elevation is just increasing as you go down and you get to EKT, the highest elevation. You can see the big difference between these two sites, right? All right, but I'm gonna just select a few things from this figure to show in more detail, and I'll start with DAII because DAII is the most studied place. So the earliest core we got here is from 1998. the Parker project. And then the next core available is from 2013. And compare these two cores, right? Although the Parker core had a more coarser resolution, it is still obvious that the density in the 2013 core is much higher than in 98. And you have much more ice layers in 2013 than in 98. So there's a huge increase in density and ice layer volume from the 1998 to 2013. And the Site J core, as you probably saw in the previous figure, the same thing goes on with that core. But what happens after 2013? Well, now it's a little more hard to see looking at a visual plot like this, what is going on. So in the next, I'm going to show you a lot of statistics too, to kind of summarize what's going on here. But I just want to point out a couple of things. Oh, a quick question. Somebody's asking if I got the cores themselves for, I got the core data from other researchers. And so the core data is publicly available, and then I have analyzed it. So I took the data from other researchers and then analyzed it in this big giant analysis. Hope that answers your question real quick. Okay, so here, okay, great. That seems like I did. Perfect. All right. Anyway, here are data from DAII. And I want to point out a few things here, because I think DAII is amazing, because it's like a place where we essentially have a time series of fern cores. And these are not easy to retrieve. Like it's considerable effort. So, but you can see here in 2013, kind of a thick layer here. And then it appears here in 2015. Maybe it's here in 2016 and here in 2017. And then after that, it's a little harder to see what happens with it. But you certainly have like thick ice layer all the way here. So you can start, even try to kind of sort of follow some regions of thick ice in over time. And I want to point out one more thing about this figure. Look in the near surface. Look in the near surface here in 2013, okay? You'll notice there are several, it's quite a large amount of ice here, all right, in the top couple of meters. Oh, I forgot to put the meter sign here. I'm sorry about that. This goes down to, I think, what is it, 25 meters or something like that. So this is just the first 4 meters or so of the core. I'm sorry, I removed the depth scale. But take my word for it. It's the top few meters. Now compare here with 2019. And you can visually see that the 2019 core doesn't have the same amount of ice as the 2013 core. And this I'm going to also show you with statistics. All right. Okay. I want to also look at 2 other sites. Okay. Because they're very interesting. And one is CONU. And this is one of those sites. This is the site that Horst Machgut in his 2016 paper were able to demonstrate this formation of very, very thick ice slabs that prevented meltwater infiltration. And in 2012, you saw surface runoff in this place where you usually don't see surface runoff. Okay, so what we're looking at here is we have this very cool, very short core from 2009, where you can see it only goes down to about 3 meters. I'm only showing you the top 5 meters here because what I want to show you is just basically the top of the ice layers. And it's very difficult actually to drill down into solid ice with, at least with the equipment we had. So if you could, so we also don't have very deep cores here. We have some, but most of them don't go very deep. So anyway, but it really a lot of interesting, actually the top 5 meters is interesting kind of because of what not happens here. All right, so I have here, you see after 2009 to 2012, you can see how all of a sudden you have this very thick layer of ice just below the surface. And I should point out a few things here with the legend. The green shaded area shows snow depth, like the winter snow depth. Blue is the ice layer. Black line is density. And gray is when there's no data. I put a red line in this figure, right? The red line is showing you a top of sort of a thick ice layer, and I define it by something that's at least half a meter thick, okay? So, and you can see, I mean, I suppose in 2012 you could debate, should it be here or should it be up there? Either way, you'll notice that the top of this thick ice layer, it remains near the surface from year to year, okay? There are some variations. There's some generation of fern here underneath the snow layer in some years. But all in all, this very thick ice layers there's probably enough meltwater percolation and refreezing to keep it near the surface at CONU site, which is the lowest elevation site. So that's quite interesting. And this is very, very, very different from the highest elevation site, which is EKT. All right, so here we see the top 5 meters of the EKT site, the highest elevation. Notice the top, just below the surface here in 2013, the top, between 1 to 4 meters. You see a thick ice layer here, one here, and so on. Then compare that with the years coming after. All right. Much less ice layers in the near surface. And I mean, the statistics will show you that the density is lower too in the years following 2013, but here you can see it visually. Okay, so I'm going to show you some intense statistics. Well, it's not that intense, but here is some statistics, okay, to kind of augment this visual analysis. All right, so what we're looking at here is we have a couple of sites, 7 sites, where there was a core collected in 2013, and there was a core collected in either 2017, 18, or 19. So I have looked at the change at those places. So it's only a few places where we have multiple cores like this. And looked at the change. So what you see here is the change in density relative to 2013. All right. Blue values means density went down. Red value means density went up. And white is just very small changes. I did this calculation on 4 depth intervals. So you'll see the first column here shows the density change between 0 and 3.75 meters below the surface. And then I go another 3.75 meters and another and another. So I have 4 intervals, and I picked down to 15 meters because that allowed me to use there were a large number of cores that was at least 15 meters. As I told you, they're all different depths. All right, and these are organized here in elevation. So we have CONU at the lowest site, DAII is this intermediate site, and EKT, highest elevation site. All right, what do we see in this figure? Well, notice the top layer. Notice the top layer here. This layer right here, okay? Every place except CONU shows decreasing density since 2013. The end year varies. Most of them is 2019, but 18, 17 is there too, okay? So there is an consistent across our study area. There is a density decrease in the top 3.75 meters. So you don't see that if you look below the surface, okay? It's not conclusive what's going on there. It goes kind of all over the place. Ice volume, and density obviously are related. Density will be affected whether or not you have ice layers there too. So if you look at this with respect to ice volume change, you see similar stuff going on here. So here's the top layer, right? All is decreasing, except CONU. And then at depth, it's a little bit different. You see this like very big increase here at the highest elevation site. That's also an artifact because of the very small, it's like the numbers are very small there. So the changes become kind of crazy. But anyway, but the big picture, the big message here is that in the top 3.75 meters, you see density decreases, ice volume decreases throughout the study area, except at CONU. All right, I think I heard somebody coughing, so you may want to check your microphone setting and make sure you're on mute, because I wasn't coughing anyway. All right, okay. All right, I'm going to show you one more thing. All right, so I showed you in the visual data how there's a strong relationship with elevation. All right, so my final piece of evidence of this density change over time is going to come from data where I have removed the impact of elevation. All right, and this is just an example of that relationship. So you see here density as a function of elevation. And here I have all the legend is showing you which year the data is from. And you can see actually the two oldest core are really interesting outliers here. All right. And you can see the red line shows the linear fit with elevation. And it's a very good fit actually, right? And also here, I'm putting in what I call the a.s.l model. That a.s.l here stands for Rennermalm model. It's a very simple model of firn densification that does not factor in meltwater infiltration and refreezing. It only factors in the impact of compaction over time. So what's interesting now is like you compare the Rennermalm model with the observations, and you'll notice, right? Up here at the highest elevation, the model meets the observations, suggesting that a model that does not include meltwater infiltration or freezing is actually a pretty good model at the highest elevation. But look down here at the lowest elevation site, it's completely off. And you know the answer because I showed you those core data that shows that down here, there's like enormous amount of ice in the Fern. Anyway, the point I want to make with this figure is that there's a very strong relationship between elevation and firn properties like density. This particular figure is the relationship for the top 15 meters of each of these cores, but this strong relationship persists regardless of which depth interval you do. So for all my four 3.75 meter intervals, this relationship holds. And it holds for ice layer volume fraction 2. So this figure here shows the ice layer volume fraction. All right. So what I did next, and this is like the last main figure I'm going to show you, and maybe also complicated, is a figure where I have removed the impact of elevation. And that gives me some really cool possibility to look at change over time where space has been removed. So now I'm going to be able to look at more data from per year because I removed the elevation impact. So it looks like this. All right. Okay, I know there's a lot of stuff going on in this figure. I'll break it apart. Top figure shows density. All right. Okay, shows density. The bottom figure shows ice layer volume and a fraction actually. And here I've removed the effect of elevation. So I've detrended elevation from all the data. And then I actually plotted the data relative to the DAII values to give you units that is that you can relate to rather than showing deviations. So that's how I got these units. All right, I shared the data here from the two legacy cores and the 2017 cores as dots for reference. There's there's not a whole lot of data from those 2 years, so I didn't want to plot it as a line. But for all the other years, I'm showing you the average of the detrended data from that year, and then the error bar shows you the standard error. So the first thing you see, which you also see very clearly when you look at the visual comparison of the two oldest core from 89 and 98 with the modern cores, is that there's a huge increase in density and ice layer volume from 1989 to 98 till 2012 and 2013. All right, but here also you really see what happens after 2012 and 2013. And what I want to put your eyes to the black line. The black line shows the near surface layer, the layer between 0 and 3.75 meters. Notice here the density is going down. Ice layer volume, it's going down. All right. Once the elevation has been detrended and you can pool all the data together, you get this strong signal of decrease. And this signal, you don't see it in the layers below, just like those other figures that I showed you. In fact, maybe it's even the opposite. You know, those thick ice layers that were formed by 2012 melt is now slowly moving down into the deeper part of the Fern core. All right, so I've shown you 3 pieces of evidence of decreased density and ice layer volume in the top part of the Fern core since 2013. We looked at a visual analysis of the cores. I looked at the change from 2013 at multiple sites. And here, finally, we're looking at the data where elevation has been removed. So, and it really fits with what's been going on since then. So I'm coming back to your own data here, where the data I've shown you is basically like 2013 to, maybe I'll draw here, 2013 to the spring of 2019 are these years. The last core was collected before 2019. This is the summer of 2019, I think. So it was collected before that summer. All right. So those years are all in the later period here since 2000. It's not, those years are not super remarkable. And we can see it even clearer if we use local data. At DAII 2, there is a weather station, and from that weather station, I calculated positive degree day sums, which is you just add up all the temperatures that are above freezing, and that's shown in these blue bars. And here, actually, you also see snow depth variation measured over time. So here you see 2012, how remarkable it is, right? This is 2012, the big outlier. And this is 2019, which was a pretty big year too, but it's not captured by our course. All right, so but look here, what's going on between after 2013 and the summer of 2019. At this weather station, DAII 2, smack in the middle of our study area. These are anomalies, so they show the deviation from the median value, ignoring the 2012 outlier. And the red stipple line shows the standard deviation. So what you see here is like those couple of years after 2012, they were either at or below median melt in this period, okay, from 1998 till 2019. So it really, the evidence of decreasing density and ice layer fraction really fits in with the larger picture of what was going on with melting. So those are my conclusions about density and ice mass in Southwest Greenland. We've seen a dramatic increase since 1989 and 98. We see a decrease between 2013 and 2019 in the near surface layer, okay? And this is co-varying with the surface melting patterns in this area. And finally, also the CONU site at the lowest elevation is different, which is actually interesting that site seems to have just transformed to a place where this thick ice layers is just able to stay near the surface every year. All right. Oh, a question about, I'll answer that question. I just noticed a question in the chat, but I'll just finish and then I'll answer that question. Okay, I just want to make one more point, and I'll point to your data again, like your absolutely excellent resource of keeping track what's going on with Greenland. So here we see the 2012 melt extent, surface melt extent in yellow. And then you see all the gray shaded areas is like the kind of median melt in the larger time period. And then you see 2019 too. And 2019 also was a big melt event year. And you have this big melt event here at the end of August. So I just want to point out that all the data I've shown you, or the bulk of my data, were collected in this time period between these two big melt years. And I think really it's sort of more of a pause than, I wouldn't say it's a trend of what's going to happen, because we all know the future is, projections are for more melting of the Greenland ice sheet. And I'm just showing you here an image from Jason Breiner's excellent paper about mass loss in a Holocene perspective, where he, so here is the, going back thousands and thousands and thousands of years, estimating mass loss. And here at the very end, you can look at the projected climate for 2100 and what kind of mass loss you'll see. And the message is it's going to be outrageous. All right. So I think the data I've shown you can show that, okay, we can have, we are in a period of increasing melting, but in that period, we can have several years that is essentially pausing the formation of this dense, ice-rich near surface firn. So that is my message for you. And thank you, NSF, for all the funding. Thank you, everybody who contributed. And most of all, thanks my team at Rutgers. Okay, that's it. All right. Hope we have time for questions.
Applause here, virtual applause and all that. This was fascinating, fascinating. So we've got some questions. It looks like a few in the chat. People have raised their hand. Maybe at the moment you could stop sharing your screen so I can see everyone. And then,
let me do that.
Let's do
stop the sharing.
Okay, we've got a few in the chat. Can you want to look at those yourself, or do you want me to read them off?
I mean, I can.
I'm not sure where you had gotten to. So.
Oh yeah. Remove. Okay, so Shri, did I say that right? Removed elevation impact by. Did I remove the elevation impact by subtracting the linear fit? I did. I did remove the. That's exactly how I did it. And the residuals are actually quite normally there. There's a little bit of elevation still, but it's pretty good. Yeah. Is the refreezing water having much of an effect on the temperature of the firn? Good question. It does have an impact on the temperature. I don't know. I mean, there's a whole field of study. I mean, there was like Hari Rajaram, right, who used to be over in Boulder. He had all this work looking at cryohydraulic warming from meltwater going into the ice sheet. I don't know. Refreezing water will influence the temperature of the firn, and we use it because we can use it to see where the water is, because you see it when the phase change. Oh, there must be water there. Does it? But I can't really speak to its potential in like changing the temperature over a year and stuff like that. But you definitely see it. You can use it as evidence of meltwater in the firn. Why not extract the melt index for your sampling area? Actually, I've done that too. I just didn't show you that one, but I have looked at. I've looked at melt index and model data and so on. But the Greenland, I think overall the patterns for all over Greenland is pretty consistent with what's going on in the melt area. which is why I show the positive degree days too, because that's very local. Proximity to the coast. It's a question about if the proximity to the coast, a possible factor at the behavior of the fern at the lowest elevation. Certainly, I mean, the large scale atmospheric patterns. I mean, I am fortunate to have working with a postdoc right now at Rutgers, Kyle Mattingly, and some of you might know his work with atmospheric river and water vapor transport over the Greenland ice sheet. And so on that very large scale, you will obviously have inputs, and that is advection of heat and moisture coming from far away over the Greenland ice sheet. But I don't know that you'll have very much local impact from the tundra. I do a lot of work in the ablation zone too, and there you definitely have sensible heat flux advection and connection with at the ice edge tundra boundary, but maybe not this far inland. Should I just continue down here?
Might as well continue. They're coming in fast and furious.
Yeah, I was like, I gotta try. All right, Mia is asking, is this meltwater storage well accounted for in remotely sensed mass balance measurement? So meaning GRACE, right? Well, I would think so, because GRACE is just weighing the whole thing from space. That's how I think of GRACE, right? It's like a giant scale, and it's like measuring the ice sheet from space. So I would think so. Of course, when it comes to using remotely sensed observations of elevation changes with LiDAR and ice bridge and ice sat and such things, then knowing the density becomes important, right? So if you assume that your fern is this porous, fluffy material, and instead it's like full of ice, then your estimates of mass balance is going to be off. Okay, more questions. I feel like the best thing about answering questions like this is like nobody can say, actually, you did not answer that very well. Just continue to the next question. All right, Mia is also asking, would you consider using GPR? Actually, if you want me to shut up because you're like, please stop talking because it's like 2 o'clock, well, noon, right? It's 2 here.
Yeah, so we got a little time. Keep going.
Keep going. I keep going. All right, would you consider, I would consider anything, but okay. Would you consider using a GPR to get an idea of small scale spatial and intra-seasonal temporal variability? Thank you for asking that question. Guess what? We did use a GPR. I just have not shown you that data because I'm leaving all of that to my excellent graduate student, Jing Xiao. So she's working on papers on that one. And unfortunately, I don't know, maybe we picked a bad choice of GPR, but it actually is like a place like DAII, it's the GPR we pick, like we don't see, it seems mostly like noise. But down at the lowest elevation at site A, B, and CONU, you can see like the big ice layers there. And you can see like over the whole study area, you see big differences. But unfortunately, the GPRs we used are not good enough to let us pick layers, which is what I was hoping we would be able to do, but we're not. And so we did transects, we did like stuff at different sites. So I think it's an excellent idea and we did it. Okay, final question or?
Yeah.
All right. Are there data available to do mass balance estimates to estimate the amount of previous seasons accumulation transfer to Iceland's mass? So we have we have for at least 2017, we have like those. So we have some years where we know what the snow accumulation is. So we have an idea of the input of mass that goes into the firn. And I mean, so it's going to be a mix of firn and ice layers. That was Ryan's questions. And Mia, yes, it is interesting. Check out, keep your eyes open for my grad student, Jing Xiao. Oh, final question. Core, what did we use? A Mac, what's it called? A Mac 3? We got it from IDDO, the IDDO, what is it called? You know, up there, Dartmouth has this drilling operations support led by Mary Albert. So we use their equipment. They have like this nice sidewinder that you can attach to the core. Did you encounter much water? We never, well, actually, should I just end with anecdotes?
Yeah. Why don't you end it with that? End it with an anecdote.
All right. So 2018 was I couldn't go in the field in 2017. So I went in 2018 and 2019, and I never camped in, you know, minus 30 degrees Celsius before, so I was a little scared of it. And but it was okay with like 2 sleeping bags, you know. But what I want to say is like 2018 was like super cold. It went down to minus 30 degrees Celsius Fahrenheit every night, and you know, everything was just cold all the time. And then 2019, of course, was like a warm year. Like so we brought ice cream and it melted. We had to like dig in our food. Like we had frozen food that was thawing. It was like so much trouble. And we also had problem with meltwater in getting our drill stuck because of meltwater forming on the surface. So in 2019, we had to get up like at 3-4 in the morning to drill at like I don't like it. I don't know about you guys, but I don't like getting up at 3 in the morning. And we had to be up, you know, super early to drill those cores, because if we didn't, our core would get stuck and we would never get it out. Of course, we have gotten cores stuck. There are like cores in Greenland that are still there. Yeah, that's okay. Not a super fun anecdote, but yes, we did have a problem with water in 2019.
All right.
Yeah.
Well, we'll have to stop it here. We're running into the end. Also, this is awesome. You're clearly a very gifted speaker. This is one of the best talks I remember in a long, long time.
Oh, so, thank you.
So I think most of us will have to go now, but this was just great. It was a real treat for us, and so we really appreciate it. So
thanks for the opportunity.
Thank
and
you.
Feel free to email me if you
yes.
anyone wants to talk more. You find me on Rutgers. Yeah.
Okay. All right. Also talk to you again. Bye.
Yeah. Thank you.